There's an interstellar object hurtling through space that defies everything we know about comets. It's called 3I/Atlas. Fresh data from the TESS satellite, unveiled on October 14, 2025, backs this up completely. By combining over 9,000 captured frames, these revelations expose what looks like a calculated effort to hide the truth. This evening, we're unveiling this compelling proof to finally crack the enigma wide open. Shifting gears from the Atlas saga, let's dive into an enigmatic star that flickers every 44 minutes across radio waves and X-rays, with scientists scratching their heads over the cause. Might it join the ranks of those bizarre celestial enigmas? We'll also spotlight 4 massive solar eruptions barreling toward our planet, potentially delivering noticeable impacts and sights in the coming days. Wrapping up, we examine the elusive neutrino, a ghost particle with such immense power that it obliterated all prior benchmarks, slamming into Earth carrying energy levels once deemed unattainable. Stick around to the finish, as the revelations we're unpacking will forever alter your perspective on the unseen watchers lurking in the shadows. If these cosmic puzzles captivate you like they do me, smash that like button and subscribe to catch every twist as these tales develop live. Share in the comments where you're watching from, the local time, and if you think we're hearing the whole story on these game-changing finds. To boost our circle, spread the word on X, Facebook, Reddit, or your personal chats. You're what fuels our pursuit of these tales, so thanks for the solid support. Part 1. TESS delivers a bombshell. Here's how it upends the basic comet narrative. Picture a velvet black sky dotted with high-tech scopes, each costing millions, all zeroed in on one elusive prize. Dozens of tools, from earthbound stations to probes drifting in the void, zeroed in on this lone intruder slicing across our cosmic neighborhood. Then, the sharpest detector among them, after merging more than 9,000 separate shots, drops a bombshell no one saw coming. It declares the thing has no tail whatsoever. On October 14, 2025, experts dropped the bombshell from an exhaustive review of TESS data, the Transiting Exoplanet Survey satellite. They'd snapped over 9,000 exposures of 3I/Atlas, the rogue visitor that's been baffling boffins since it popped up. By layering those shots via co-adding, a method built to tease out subtle hints from the clutter, you amplify the glow incrementally, frame after frame, until even the subtlest outlines pop into view. It's akin to catching a faint melody and cranking the amp with every loop until the tune rings clear. What TESS revealed, or more precisely, failed to reveal, was mind-blowing. The intruder showed up as a mere pinpoint, a speck with no sprawling haze, no hazy veil of debris and vapor fanning out, no streamer trailing sunward. Probing its radial light profile, the way intensity fades from the core, it mimicked a distant star's drop-off, not a comet's. Stars shrink to pixels from sheer distance, despite their vast scale. Comets ought to behave otherwise, expanding, revealing form, flaunting that legendary streamer that sparked awe and dread across ages. The point spread function, or PSF, captures the light smear from a pinpoint after optics filter it, a unique signature for each scope. When TESS scrutinized 3I/Atlas, all it detected was that signature, zilch more. The researchers nailed down the implications precisely. Any dust past a set brightness threshold would have shown up. That stacking boosts the signal-to-noise so intensely that even dim traits emerge. They crunched limits on dust concentration, grain dimensions, and spew speeds. Every figure converged on one verdict. Any potential dust isn't acting like typical comet fare. Yet contrasting sightings paint another picture, and that's where the weirdness ramps up. The James Webb Space Telescope, JWST, picked up traces of water vapor and CO2 encircling it. Spectral scans indicate material shedding, gases venting into the ether, clear hallmarks of cometary action. So why no tail? Where's the tangible proof of all that outflow? This paradox pins you down. The haze must be extraordinarily tight, so packed and restrained that it's undetectable in visible light, yet it yields gaseous clues, or perhaps an altogether different process is at play. It's reminiscent of a blazing hearth with zero rising plume. Either the fumes are squeezed out of sight by some unknown force, or the blaze we're observing isn't combustion in the usual sense. The clash looms inescapably. Researchers devoted months peering at this entity, using one of the finest tools we've constructed yet for spotting subtle, sprawling features. It detected zilch. Yet devices calibrated for varied spectral bands and distinct physical phenomena are yelling that activity is undoubtedly underway. Something essential is absent from one of these datasets, or our whole model of comet appearances is on the verge of crumbling. And this is what haunts my sleepless nights. Comets have pulled off odd behaviors in the past, but nothing quite like this. No object has ever so convincingly posed as a pinpoint emitter while displaying clear signs of intense chemical processes. The figures don't merely refuse to align, they outright clash. This goes beyond a small inconsistency attributable to varying observation setups or device anomalies. It's a core conflict over the entity's behavior. The test results are now openly available. Anybody can grab them, perform their own review, verify the data. The outcomes hold up under repetition. The absence of a tail is rock solid, so we must unravel what's occurring. If standard comet dynamics can't account for this, we'll have to entertain ideas that feel oddly unconventional. But first, we need to gauge the depth of these inconsistencies and explain why various tools are depicting entirely divergent views of the identical body. Part 2. Clashes across instruments. JWST, terrestrial arrays, spectrographs. Imagine JWST, the $10 billion gem of infrared observation, directing its reflectors at 3I Atlas. The data returns, and it's unambiguous. Carbon dioxide, water vapor, a gaseous envelope brimming with volatiles. The spectrographs capture molecular traces. Emission spectra indicate atoms getting energized. Molecules are oscillating, gases streaming away from the core. At the same time, Earthbound visible light scopes spot asymmetries, or, in certain instances, barely anything. Diverse tools, conflicting narratives. What's the deal? Part of the explanation rests in what each device truly gauges. JWST functions in the infrared, targeting bands where molecules release radiation during vibrations and rotations. It's exceptionally attuned to gases, to the makeup of whatever's drifting near the nucleus. It doesn't rely on bounced sunlight to identify a coma. It's tuning into the molecule's infrared chorus, and that melody rings out strong. SphereX, a further infrared endeavor, has noted substantial quantities of vaporized carbon dioxide encircling 3I Atlas, with CO2 to water proportions that stand out even among the quirkiest comets. Visible telescopes operate otherwise. They're examining sunlight bounced back, how dust grains diffuse solar rays our way. To discern features in a visible picture, you require dispersed dust. You need grains distributed across volume that can snag and reroute sunlight. Should the dust be overly dense, too near the nucleus, or if the grains are ill-suited for scattering at visible wavelengths, you could see next to nothing, despite gases gushing from the body. Enter scattering properties. Tiny dust bits, micron-scale flecks, diffuse light well, and can craft noticeable tails. Bigger ones, from millimeter to centimeter sizes, scatter less effectively and drift more sluggishly. Their greater heft makes them tougher to eject from the nucleus. Such hefty grains could linger nearby, forming a tight, yet optically dim sheath that visible scopes find hard to pick up, though it still yields ample gas as surface ices turn to vapor. Geometry plays a role too. The phase angle, the span between sun, object, and viewer, alters our view of any tail or coma. Viewed from an awkward perspective, a tail might appear shortened, aimed nearly straight at or away from us, making it practically undetectable even if present. Various instruments scanned at separate moments, from distinct orbital spots, catching the object at varied angles. A tail evident to one could evade another due to sheer positional misfortune. We've witnessed such inter-tool disputes previously. Comet Ison in 2013 was forecast as dazzling, only to shatter, with scopes reporting fluctuating activity levels over time. C/2017 K2 displayed a coma in select views and seemed subdued in others, fueling arguments over its true vigor or sporadic outgassing. The contrast here is the magnitude. Atlas isn't merely varying, it's bifurcated. Tail present or absent, point-like or spread out. Observations offer scant in between. The scheduling disparities exacerbate it. JWST scanned in specific slots, ground telescopes during even with ground-based setups and other instruments. TESS kept watching nonstop, though its detail on spatial scales was more limited. Imagine if the target object only activates sporadically, ejecting clouds of dust and gas in sudden spurts instead of constant flows. In that case, one scope could spot it right in the midst of a flare-up, while another might just glimpse the remnants. The data would seem at odds, despite both being spot-on for their specific timings. Yet, after factoring in all such variables, the degree of inconsistency stands out. Combining stacks of optical photos from expert facilities ought to reveal subtle dust patterns if they exist. That TESS, after processing thousands of exposures, detects no spread-out features points to the dust being remarkably confined, or perhaps absent in the amounts we'd anticipate. And without it, what's generating all that gas? It doesn't materialize out of nowhere. Typically, it arises from ice vaporizing on dust particles or straight from the core itself. Both mechanisms would kick up dust too. At this point, you begin questioning the reliability of any one tool. They're each grasping a fragment of the puzzle, dutifully conveying what their unique detectors pick up. But stitching it all into a unified image isn't happening. It's staying fragmented. That's usually how cosmic riddles unravel. You collect extra info, tweak your theories, and spot an overlooked factor, like odd light-scattering traits or atypical makeup. However, each fresh look at Atlas only deepens the confusion rather than sharpening the view. And that leads us to the probe angle. The data that could potentially sort it out might instead amplify the chaos. There's an apparatus that could have offered the ideal vantage, the sharpest clarity, the optimal alignment to glimpse Atlas in detail nearby. The Psyche probe was in position. Its path could have positioned it for a clear shot. So, if it snapped any photos, what's the holdup on releasing them? Section 3. Chronology and the Psyche angle. The point where Psyche slots in and the official logs fall silent. We've reached a dead end with terrestrial and orbital scopes clashing over their sightings. Time to address what could be the key sighting that stayed under wraps. The Psyche craft, sent aloft by NASA to probe the iron-heavy asteroid 16 Psyche, has been cruising the space between planets equipped with a range of photo-capturing gear. Its goal is the main asteroid, but en route, the onboard cameras snag routine test shots, guidance pics, and chance extras for research. The vessel includes a camera suited for high-detail snaps. In transit mode, the ops crew often aims these lenses at assorted objects to check functionality, fine-tune gear, and snag incidental knowledge when chances pop up. This is routine for deep space voyages. With lenses handy and the void zipping by, you snap what you can. NASA has shared a few of these publicly, test views of our planet and its satellite from afar, star maps for route checks, things like that. Now, the schedule turns intriguing. Drawing from open orbital charts, the routes and spots of Psyche alongside 3I/Atlas reveal periods when the cosmic wanderer could have been in the probe's potential sightline. Not right next door, but near sufficient for a deliberate aim to yield valuable info. The precise setup hinges on calculable flight dynamics from released mission specs, yet the chance is real. So what about those shots? NASA holds vaults of unprocessed voyage records. Most orbital projects eventually drop their raw visuals or at minimum details on captures and timestamps. These troves let hobbyists unearth comets or rocks in vintage frames sometimes. They allow experts to revisit and uncover overlooked gems post-first review. Psyche's unfiltered camera outputs should surface in NASA's Solar System Data Repository or dedicated voyage files. The puzzle lies in no announced drop of unprocessed Psyche frames featuring 3I/Atlas near flyby times. This might signify various scenarios, so we should avoid hasty leaps. Let's explore the innocent rationales up front, as they're entirely reasonable. Transmitting probe info is bandwidth limited. Far-flung operations can only relay limited volumes per Earth link-up slot. Controllers rank what flows back. Tech stats lead, followed by core task research, then the rest. If Psyche's lenses grabbed Atlas frames, they could be queued in onboard storage, awaiting a later downlink slot with spare capacity. There's the issue of storage limits and data handling to think about. Probes in space can't store endless amounts of info. They rely on circular buffers that erase older files once fresh ones arrive. Unless Atlas shots were marked as top priority, they could have been squeezed down a lot or even replaced by subsequent scans. This sort of thing occurs way more frequently than most folks appreciate. Not all shots from a cosmic probe reach our planet in complete detail. Another angle involves glitches in metadata and cataloging. Those pictures might be tucked away in the repository but not indexed correctly. Faulty timestamps, incorrect labels on observation zones, damaged file headers. These are common. Folks familiar with massive stargazing databases understand how data can vanish in practice, just from poor filing or mismatched tags. A snapshot of Atlas could be lurking there, tagged as a test image or a starry backdrop, overlooked until somebody spots the real content. Don't forget the administrative side. Agencies running space ops impose hold times, rules on data ownership, and phases where only the core team gets access. It's possible the shots are there, the crew is poring over them, and the rollout timeline just hasn't hit yet. Research groups typically claim initial dibs on their findings before going public. This safeguards the experts who crafted the gear, letting them drop papers first so others don't beat them to the punch with identical info. Each of these ideas makes sense on its own. None demand plots or hidden agendas. They're simply the everyday hurdles in space exploration workflows. Yet, keep this in mind. Lacking proof doesn't prove it didn't happen. We can't tell what got recorded since the whole collection isn't viewable. We have no clue on what got beamed down first, what faced heavy compression, or how items were tagged. The details that could clarify might be spotty or locked away themselves. What we ought to pursue, and indeed must, is to inquire. Requests under the Freedom of Information Act can force out official data. You can submit bids for archive entry, logs from missions, SLOH records, gear performance summaries. These materials are out there and obtainable. The core puzzle remains. Are those shots that could crack the Atlas enigma stashed in some vault, ready for unearthing? Or did they never get taken? Or were they snapped but withheld for motives still unclear? From here, the narrative branches wildly. Should the images surface and go public, we could at last glimpse Atlas's true form, clearing up clashes between TESS, JWST, and the rest. If they're absent, we'd have to unpack why a craft with functional optics skipped what could be this era's stellar highlight. And if they're present yet unreachable, that sparks a whole other challenge, probing openness and oversight in cosmic research. Section 4. Other physical options besides Comet. Ideas that aren't comet-based but match the observations. Let's pull away from the data hunt and tackle a deeper query. Suppose 3I/Atlas defies comet norms entirely? What if we've shoehorned it into the incorrect box right from the outset? If it bucks comet behavior, what other possibilities fit? And could any rival theory hold up against the stack of limits we've assembled? Idea 1. A hefty inactive mass with tiny gas leaks. Picture a slab of stone and frost from a distant stellar neighborhood, molded by alien brewing processes unlike our system's natives. Perhaps it's largely dormant, not boiling off material comet style, yet leaking modest gas via fissures or isolated volatile ice patches on the exterior. That accounts for the gas traces JWST detected, minus the huge dust output that'd form an obvious trail. The thing remains dense and dot-like in views, yet displays some chemical fizz. This setup's hitch lies in gauging the gas output levels. JWST data points to notable volatile escape. You can't conceal that volume of gas from minor fissures without stirring dust too. Frost doesn't evaporate neatly. It hauls grit along as it turns to vapor. To dodge that, you'd require an odd makeup, like pristine volatile layers somehow isolated from particles. But that feels shaky in geological terms. Idea 2. A debris cluster. What if 3I/Atlas isn't one solid piece, but a dense pack of tinier bits cruising in sync? Each too faint to pick out solo, even through top-shelf scopes, yet together yielding the glow we detect. Envision it as a pod of fish or a bird formation, acting as one cohesive body. Every shard ejects a bit of gas, a touch of dust, but the stuff lingers inside the group instead of fanning out in a standard tail. This might justify the compact, spot-on look. If the shards of sources are positioned so closely that they exceed our ability to distinguish them angularly, they might appear as one unified entity. The release of gas could spread out over numerous tiny areas instead of originating from a central core, possibly leading to scattering behaviors that differ from our predictions. Yet this idea comes with its own issues. How would these pieces remain connected? They'd require a shared gravitational influence, or else they'd separate across vast cosmic expanses. Plus, a cluster like that ought to display some form of irregularity, like stretching or a hazy outline, even if we can't make out the separate elements. Next up, Hypothesis 3, electromagnetic influences. Here's where we venture into the unusual. Imagine the dust grains near Atlas holding an electric charge, influenced by a robust magnetic or electric field that keeps them tethered to the core. Electrified particles can float, get locked into patterns that defy basic orbital paths. We observe this in Saturn's rings, in controlled plasma setups, and in zones where electric forces outmatch gravity. Should Atlas bear a charge or produce fields via an unknown method, the dust could avoid forming a trail altogether. It might linger, orbit steadily, or stay contained. Gas would still vent out, as neutral molecules resist electromagnetic capture, but the dust could remain hidden, undetectable by visual scopes searching for sprawl. This scenario accounts for nearly all the puzzles: the tight profile, the gas signals, the absent trail. The downside: we lack any clear way for a passive entity to create those fields. It would demand activity, some power source at work. That leads to Hypothesis 4, the one that leaves experts uneasy, yet we must entertain it amid all this oddity. Suppose this thing is man-made? What if it's constructed, equipped with operational tech that yields the signals we're detecting through engineered means, not natural ones? A crafted item could resolve the paradoxes seamlessly. Dynamic mirrors might cause the light fluctuations. Power units could release gases sans ice vaporization. The solid form would suit a built design. Any electromagnetic traces, if present, would seem routine, not enigmatic. Of course, this bold assertion demands ironclad backing. And right now, we lack it. We have quirks, inconsistencies, baffling data, but no confirmation. Each theory offers testable forecasts. The mini-outgassing idea suggests we'll spot subtle dust output eventually, dim yet catchable with accumulated data. The debris group theory anticipates shifts in form as the collection changes. The electric force theory expects detectable field signs, odd polarizations, perhaps radio signals. The constructed theory foresees unnatural features, precise geometries, emission lines from tech operations, rhythms hinting at intent over randomness. What's striking is how no theory fits flawlessly. They clarify certain data while sparking fresh doubts elsewhere. Everyday natural accounts hinge on improbable makeup or setups. Wilder natural ones rely on comet physics we've yet to witness. And the built one asks us to embrace alien tech, a step few experts take absent decisive proof. Still, we'll need one of these, or something wilder, since the classic comet framework has crumbled. We can't label it a comet forever if it keeps defying the rules. Eventually, when something repeatedly bucks your assumptions, you must revise your view of it. Atlas may have reached that threshold. Section 5, Outlining the Test. What would solidly demonstrate it's not natural? Let's set clear boundaries. Let's pinpoint the evidence needed to dismantle natural theories and compel us to weigh artificial origins seriously. This shifts from guesswork to crafting verifiable standards that could sway doubters. Criterion 1. Detailed form defying established science. If we imaged Atlas sharply enough to reveal its outline, and that outline featured crisp lines, 90-degree corners, balanced designs, or shifting sections, it'd raise alarms. Organic forms are uneven, rough-hewn by build-up, impacts, and pulls that avoid tidy shapes. A round body raises no flags. Globes optimize energy. But a box, tube, or linked pieces in motion, those cry out for answers. Criterion 2. Clear-cut spectral signatures from substances not naturally occurring. Comets typically display signs of water, carbon dioxide, carbon monoxide, and various organic compounds, elements consistent with ancient origins. However, detecting technium, which arises solely from nuclear processes, or spotting industrial substances like synthetic polymers or unnatural isotope distributions, would raise serious concerns. The cosmos generates a finite array of materials via stellar nucleosynthesis and chemical reactions. Deviations from this array require thorough explanation. The third standard involves irregularities in multi-wavelength alignments. Capture visuals across various spectral ranges and superimpose them. Typical celestial bodies exhibit expected behaviors. Warmer areas radiate excess infrared, particles diffuse visible light, and gases glow at precise frequencies. Should the overlays fail to match physical principles, or if features appear in one spectrum without counterparts in others, this points to phenomena beyond basic heat and diffusion effects. The fourth measure concerns data origins and instrument logs. For satellite-derived insights, unprocessed images ought to include tags with timestamps, device configurations, integrity checks, and adjustment records. Such details allow confirmation and comparison with operational records. Discrepancies might signal manipulation, yet reliable, confirmable tags bolster any assertion regarding the sighting. Extraordinary discoveries demand authenticated records. The fifth aspect encompasses synchronized signals spanning diverse physical realms. Suppose Atlas exhibited concurrent visual flares, radio pulses, X-ray bursts, and neutrino spikes, all precisely timed to identical incidents. That would be extraordinary. While natural events yield emissions across wavelengths, they adhere to familiar profiles. Quasars, pulsars, and supernovae each bear distinct markers. An utterly unprecedented pattern in cross-spectrum activity would necessitate fresh theories. Past cases illustrate how evidence reliability and traceability can validate or undermine bold assertions. The Apollo mission's recordings were almost erased, necessitating recovery work years afterward. Portions got overwritten or deteriorated. In astronomy, repositories have faced similar troubles: misidentified files, failing media, and expertise vanishing with retiring experts. The caliber of proof rivals the proof itself in importance. Social dynamics factor in too. Project groups endure intense scrutiny. Reputations hinge on effective operations, credible publications, and defensible statements. Geopolitical motives matter. Certain records may remain restricted or withheld for non-scientific purposes. The dread of mockery persists. Researchers avoid being the one to proclaim extraterrestrials erroneously. The stakes are steep. Thus, a trustworthy dataset would feature unedited, full-resolution captures, untouched by adjustments. Full tag sets verifiable via external references. Integrity verifications ensuring no modifications. Numerous separate readings from varied tools that align consistently. Public availability enabling scrutiny and replication by others. And preferably, a clear record of handling from acquisition to archiving to distribution. Every recording, assertion, or disclosure about Atlas merits this scrutiny. If a claim involves probe visuals depicting the unusual, initial queries should seek the original captures. Are the tags checkable? Can external experts examine the files? Absent such openness, it resembles yet another vague sighting that sparks more doubt than clarity. The onus for validating a remarkable statement is immense, as it must be. Scientific advancement thrives on stringent proof, replicability, and rejecting allure in favor of verification. Yet progress also stems from pursuing oddities, crediting misfitting data, and revising frameworks when compelled. Currently, the Atlas findings intrigue enough for deep investigation but lack the sharpness for definitive judgments. Future steps rely on obtaining key visuals, whether fresh insights resolve uncertainties or amplify them, and if experts weigh doubt against inquiry appropriately. The guidelines exist. The benchmarks are set. We await the proof's arrival. Section 6. ESCAP, J. 1832. A 44-minute pulse in radio waves and X-rays. Let us briefly shift focus from Atlas to an event within our Milky Way galaxy, compelling stargazers to reassess their assumptions about space entities. Researchers employing the Australian Square Astronomers using the ESCAP radio telescope array and NASA's Chandra X-ray Observatory have spotted an intriguing entity dubbed ESCAP, J. 1832-0911. This thing emits pulses reminiscent of a heartbeat, occurring every 44 minutes in both radio emissions and X-rays at the same time. The find emerged during a search for fleeting radio signals, those elusive sources that pop up, fade away, or fluctuate in intensity periodically. Long-period transients, or LPTs, represent a fresh class of cosmic phenomena that flicker in radio frequencies on scales from tens of minutes to hours. Such objects are scarce, baffling, and refuse to slot into established categories. ESCAP J1832 stands out as the inaugural example caught pulsing in X-rays alongside radio waves, rendering it exceptionally peculiar. The measurements are spot on. It releases a 2-minute surge of radio signals, followed by 42 minutes of silence, then repeats the pattern with impeccable precision. Chandra's data reveals X-ray emissions aligned with the radio flares, not exactly coinciding, but clearly linked. The source is pinned down to about 15,000 light-years from us within the Milky Way, yet it doesn't align with any prominent star cluster or gaseous cloud. What might generate this rhythmic emission? Prime candidates include highly magnetized celestial bodies. Magnetars, those neutron stars boasting extraordinarily intense fields, are famous for their pulsing behavior. However, their typical rhythms are far quicker, spanning milliseconds to seconds rather than 44 minutes. Achieving such a leisurely pace would demand an unconventional setup, perhaps one where the magnetic energy builds gradually before unleashing in bursts, and no solid theory accounts for that so far. Another contender, ultramagnetized white dwarfs. These remnants of deceased stars have shrunk to roughly Earth's dimensions while retaining robust rotation and potent magnetism. A white dwarf rotating every 44 minutes, uncommonly sluggish, and experiencing sync accretion or magnetic flares tied to its spin could produce recurring signals, though the cadence remains odd. Usually, white dwarfs whirl much more rapidly or shed their magnetic properties altogether. Perhaps a binary pair offers a better fit. Imagine two bodies circling one another every 44 minutes, with interactions like material transfer or tidal forces sparking regular outbursts to match the data. The catch? Such a tight orbit means they're perilously near, likely destined to collide soon or spiral inward swiftly from gravitational waves. Standard theories fall short here, each demanding adjustments to variables, rare scenarios, or rationales for awkward data points. And that's without even bridging it to Oumuamua, which appears unrelated at first glance. ESCAP J1832 is a Milky Way resident, seemingly stellar, flashing in radio and X-rays. Oumuamua, by contrast, is an interstellar wanderer displaying oddities in visible and infrared light, sans verified radio or X-ray activity. They seem wholly distinct events in disparate settings. Yet, that's precisely the point worth pondering. If a single galactic oddity can shatter conventional frameworks, generating emissions that defy known cosmic types, we ought to approach judgments on bizarre encounters with more humility. ESCAP J1832 demonstrates the cosmos retains surprises beyond our inventories, processes we can't yet grasp, and undiscovered object types lurking undetected. The breakthrough also underscores our observational blind spots. ESCAP, a modern radio array, has only been active for a handful of years. Chandra launched in 1999, yet it captures merely what we direct it toward. ESCAP J1832 has likely been throbbing for eons, thousands or millions of years, and we only caught on recently. Countless other enigmas must exist, within reach of today's instruments, simply awaiting the proper scrutiny or vantage. This ties directly to Oumuamua, shifting our baseline assumptions. Prior to ESCAP J1832, one could argue that natural bodies rarely produce bizarre, multi-wavelength periodic signals, tagging such reports as glitches or errors. Now, with evidence of these signals and zero explanatory models, we must rethink knee-jerk rejections of outliers that buck the norm. It points to a smarter investigative path. Spotting one irregularity should prompt hunts for more, checking for emerging links. There may or may not be ties, but ignorance persists without effort. This leads to the core query. Might Oumuamua and ESCAP J1832 share some underlying physical principle? It borders on the ridiculous, but let's probe it fairly before waving it off. Section 7. Potential ties. Is there any feasible physical bond between ESCAP J1832 and Oumuamua? Let's state plainly from the start. Nothing links ESCAP J1832 and One-Eye/Oumuamua in any demonstrable fashion. Their diff were delving into various kinds of entities, ranging from diverse sizes to distinct settings. Our approach here involves examining parallels, seeking out possible common underlying principles, and questioning if similar unusual physical phenomena might function across varied scenarios. Even if the conclusion turns out negative, the process of pondering these ideas sheds light on the experiments worth conducting. Begin by considering energy levels. The object designated APJ-1832 emits radio waves and X-ray bursts. Such radio signals might arise from synchrotron radiation, where charged particles curve through magnetic fields, or from synchronized plasma interactions. X-rays demand much greater energies. These could stem from heated plasma, magnetic field reconnections, or particles speeding up to near-light velocities. All these represent vigorous activities, vastly more intense than the mild solar warming of ice and stone we link to comets. Yet, imagine if Atlas possesses or produces its own magnetic fields. Comets indeed develop induced magnetospheres. As solar wind encounters their ionized gas envelopes, the effect is subtle. It's nothing comparable to the structured fields in magnetars or accreting systems, but the phenomenon occurs. Should Atlas harbor an exceptionally robust internal magnetic field or transport charged particles that form field patterns, might those conditions generate radio signals appropriately? Insights from plasma physics offer intriguing options. Synchronized radio output can emerge from plasma disruptions, zones with abrupt shifts in charged particle concentrations, or interfaces where plasmas clash. As Atlas releases gas, solar ultraviolet radiation ionizes it. This creates an ionized envelope, a plasma, that can sustain waves, disruptions, and radiation processes. Typically, these signals are too faint for detection, but in rare circumstances, like elevated charge concentrations or atypical magnetic setups, observable emissions could occur. However, the rhythms differ dramatically. ASEP J1832 exhibits pulses every 44 minutes with remarkable consistency. This pattern implies spinning, orbital paths, or resonant vibrations. In contrast, Atlas's visual data reveals no such rhythmic patterns. Any repeating features appear on scales of days or weeks, not minutes. Thus, a mutual process would need to function over an enormous span of timescales, which feels improbable without a fundamental mechanism that adapts variably to diverse surroundings. Regarding X-rays, we've observed X-ray output from comets previously, arising from solar wind ions swapping charges with neutral atoms in the gas envelope. It's subtle, demanding advanced detectors, but genuine. Should Atlas feature a particularly thick or dynamic envelope, X-ray signals wouldn't shock. The key issue is if that output shows periodicity, organization, or alignment with other detected phenomena. Standard charge exchange tends to be steady, without pulsing. Now, let's explore a cohesive conjectural idea. Purely as an intellectual exercise, envision a category of bodies, whether natural or artificial, that sustain intense localized magnetic fields alongside concentrated plasma zones. On galactic scales with massive, dense entities, you end up with ASCAP J1832, steady pulses from spinning or vibrating radio and X-ray signals via plasma dynamics. In a smaller, interstellar setup like Atlas, the identical field and plasma principles apply, but express as bounded gas envelopes, odd gas-to-dust proportions, and perhaps radio flares too dim or fleeting for prior notice. This idea yields verifiable forecasts. If Atlas and ASCAP J1832 draw from the same physical roots, we ought to search for subtle radio pulses from Atlas, particularly near perihelion when solar wind effects peak. X-ray bursts linked to visual flares or gas outbursts. Polarization patterns in Atlas's reflected light hinting at structured magnetic fields. Faraday rotation in radio sources viewed through Atlas's envelope, disclosing field intensities. Neutrino signals tied to either if acceleration yields high-energy particles. Many of these checks remain unperformed or unpublished. Radio arrays haven't routinely tracked Atlas at fine temporal scales. X-ray instruments may not have targeted it amid outbursts. Evidence to validate or dismiss the link could simply be absent so far. The analogy proves beneficial regardless of outcome. If monitoring Atlas at radio frequencies, next time it's active yields no results, that bounds theoretical frameworks. It indicates absence of synchronized plasma radiation, no synchrotron effects, no radio-generating processes at work. Such data holds worth. It discards possibilities. And should we spot radio pulses, X-ray links, or predicted markers, that'd be groundbreaking. It'd imply Atlas behaves way beyond typical cometary norms, forging ties to dynamic stellar phenomena like ASCAP. Pushing into that realm would land us squarely in the realm of the bizarre, where standard theories fall short and we're forced to grapple with ideas we'd prefer to avoid. The key is approaching this methodically. Oddities in one phenomenon can shape our perspective on quirks in others. By examining various events side by side, recurring themes start to surface. And occasionally, the most outlandish links prove valid, since the universe applies identical physical principles across diverse scenarios. We'll only discover the truth by investigating thoroughly. Part 8. The 220 PeV phantom particle. Why one neutrino packs such a punch? Everything shifted because of a lone particle. On what ought to have been an ordinary day, far below the Mediterranean's surface, the KM3 net detector network captured an event that defies our cozy grasp of cosmic ray mechanics. A neutrino boasting 220 peta-electron volts of energy barreled through the setup, generating a luminous streak that revealed insights into the cosmos's most ferocious events. Allow me to break down the significance, as figures this immense strip away their everyday sense. 1 peta-electron volt equals a quadrillion electron volts. The protons circulating in the Large Hadron Collider, humanity's mightiest particle smasher, top out at roughly 14 tera-electron volts. This neutrino hauled 16,000 times the punch of those protons. It's like a stellar projectile unleashed by a force so immense that our theories for it remain incomplete. Neutrinos act as elusive phantoms. They glide past everyday stuff without a hint of resistance. At this very moment, trillions from the sun are piercing your frame, tunneling through the planet, and sailing onward into the void, untouched by any atom. Nearly massless, electrically neutral, and lacking traits that snag them on regular particles, they're incredibly hard to spot. Pinpointing them demands vast expanses of clear substances like ice or water, rigged with detectors that scan for those infrequent collisions where a neutrino sparks a charged offspring, which then outpaces light in that setting and glows. KM3 net leverages the Mediterranean's depths, turning the ocean into its vast sensing chamber. Suspended strings of photodetectors survey cubic kilometers of seawater, alert for the distinctive glow of Cherenkov radiation marking a neutrino strike. The specific module that flagged this incident traced the telltale muon trail, reconstructing the sequence to confirm the neutrino's energy hit at least 220 PeV. Peer review has validated the findings. No error, no false positive. It's genuine. So why the fuss? Neutrinos, this energetic signal cosmic engines cranking at levels that stretch our comprehension. Prime suspects include blazars, supermassive black holes devouring material at galactic cores, spewing near-light-speed plasma streams. Such outflows can supercharge protons to insane velocities, and when those protons smash into stray light or debris, they spawn pions that break down into neutrinos. Gamma-ray bursts, the final agonies of colossal stars imploding into black holes, offer another avenue. Any setup capable of such particle boosts dances on the edge of known physics. Now, the intriguing tie-in. Slim, yet intriguing enough to probe. Might Oumuamua be linked to, or traversing, a zone of extreme astrophysical intensity? It originated from beyond our solar system. Its general path is mapped, letting us backtrack toward the galaxy's heart, though its full voyage remains a mystery. Did it skim a supernova's aftermath, a pulsar-driven nebula, or cosmic patches laced with intense magnetic fields and dense plasmas that foster particle boosts? The idea escalates. Should Oumuamua harbor unfamiliar matter, forces, or traits we've missed? Might it clash with the solar breeze or space's ambient mix to generate ultra-energetic particles? Could it trigger neutrino bursts via processes absent in typical comets? This might seem far-fetched at first blush, but recall, we truly don't grasp Oumuamua's nature. We label it a comet due to its solar system visit and hints of outgassing, yet every aspect screams anomaly. There's a solid way to test it. Neutrino observatories like KM3 Net, IceCube in Antarctica, and their peers run nonstop surveillance. Their logs carry precise timings and directional data. Should a surge of ultra-high-energy neutrinos align with Oumuamua's closest solar approach, its outburst periods, or any oddities we've noted through telescopes or spectra, that overlap would demand attention. Random alignments can be statistically weighed. A robust match would imply a real bond. Precedents exist in other cosmic hunts. When IceCube pinpointed neutrinos from during an energetic outburst from a well-known blazar, the detection verified that these objects truly emit neutrinos. The breakthrough in multi-messenger astronomy depends on linking signals from various particle types and emissions, including light, neutrinos, and gravitational waves. Every type of signal reveals distinct details about the origin, as they're generated through unique physical processes and propagate across the cosmos in their own ways. Neutrinos stand out for their remarkable ability to evade obstacles. If they're originating from something like Atlas, they would stream out unimpeded, delivering direct clues about the underlying mechanisms creating them. In contrast, gamma rays could get blocked by interstellar dust or gas, while radio signals might get deflected. But neutrinos barrel straight through all matter, reaching our planet with a clear trajectory back to their birthplace. They serve as the premier cosmic informants for peering into regions shrouded in mystery. That 220 PV observation serves as evidence that these elusive signals exist, highlighting a cosmos brimming with ferocious, immense forces capable of spawning them. It's a nudge that our inventory of universal events remains partial. We still haven't uncovered every method nature uses to hurl particles to extreme speeds, forge magnetic fields, or unleash intense radiation. Fresh kinds of celestial bodies and processes continue to emerge. Thus, when examining Atlas amid its puzzling quirks and inconsistencies, remember the universe has repeatedly surprised us with unforeseen behaviors. A SCAP J1832-04 flickers in patterns that baffle existing theories. A neutrino packing inconceivable power emerged from an unknown spot. Black hole collisions spawn gravitational ripples that we only started spotting about 10 years back. The roster of cosmic oddities just expands. Perhaps Atlas is merely a comet boasting an odd makeup, and we're reading too much into it. Yet it could also join the lineup of unanticipated wonders. Yet another puzzle demanding fresh theories or entirely new frameworks to decipher. The sole path to clarity involves persistent monitoring, cross-referencing signals, and probing potential links between disparate oddities. Achieving that demands full access to every dataset, even those tucked away in storage awaiting scrutiny. Part 9. Space Weather Impacts. 4 CMEs, Aurora Predictions, and the Role of Local Conditions. As we've delved into far-off entities and rare particles, a nearer phenomenon has been stirring up trouble for skywatchers: the sun's ramped-up activity. In rapid sequence, for coronal mass ejections have blasted toward our planet. Slated to impact between October 15th and 17th, 2025, these colossal billion-ton blobs of charged, magnetic solar material hurtle through the void at speeds of millions of kilometers per hour. Upon slamming into Earth's magnetosphere, they spark geomagnetic disturbances. For those chasing northern lights, this spells thrilling prospects. Such storms funnel energized particles into the planet's polar upper layers, where they smash into air molecules, igniting the ethereal veils of color known as auroras. The fiercer the disturbance, the more equatorward the displays stretch. Predictions for these CMEs suggest spectacular auroral shows that could dazzle viewers at temperate latitudes. Yet for stargazers aiming to capture dim targets like Atlas, solar activity turns into a major headache. The very particles fueling those stunning lights also generate interference. Radio telescopes suffer from ionospheric twinkling, where turbulent charged layers make signals dance and weaken, far more disruptively than a star's simple scintillation. Bursts of cosmic rays ramp up, peppering instruments with bogus readings. In visual astronomy, atmospheric glow from aroused gases adds unwanted haze to exposures. Satellites endure outright hits too. High-speed solar bits can scramble digital circuits, mangling records or sparking phantom alerts. Orientation systems relying on star patterns get thrown off by particle strikes mimicking extra stars. Imagers display random flares, faulty spots, or lines from ray impacts. Data handlers must scrub all this out, though the cleanup isn't always flawless. This is where things turn tricky. Solar events offer easy cover for data glitches. Absent images in records, bizarre flaws in shots, or breaks in logs. It's simple to pin on the weather up there. A CME struck right during the session. Particle barrage wrecked the files. The probe entered protective standby amid the flux. These are real issues that occur routinely, but they double as handy alibis. So how do you tell true solar fallout from other causes of spotty or flawed info? Scrutinize the traces. Solar disruptions mark clear patterns. Ray strikes show up as pinpoint flares in isolated pixels or tiny groups. Ionospheric effects, it reveals typical time frames and how frequencies play into it. Safe modes on spacecraft produce distinct telemetry signatures and log records. With complete metadata at your disposal, pinpointing the issue is usually straightforward. The real challenge arises when that access is denied. If you're just informed that data vanished because of space weather, minus the granular logs, instrument checks, pre- and post-calibration images, validating the statement becomes impossible. It could hold water. It might represent a watered-down version of a thornier reality, or it could mask an altogether different issue. This isn't mere suspicion, it's the bedrock of data reliability. Scientific assertions demand checkable proof, and proof hinges on clear origins. You must trace the data's source, its handling steps, and any incidents during transit. Once breaks emerge in that accountability trail, or when accounts stay fuzzy or partial, the data's trustworthiness dips, limiting its use for bold assertions, be they routine or groundbreaking. Plenty of past cases illustrate this. The Hubble Space Telescope's NICMOS instrument suffered a cooling breakdown initially pinned on broad thermal glitches, yet it stemmed from targeted mechanical faults that demanded years to unpack fully. Mars Observer vanished amid orbit insertion, telemetry hinting at a propellant line breach, but the patchy records fueled rival hypotheses. Incomplete datasets breed unclear interpretations. For Atlas data, this carries weight since we're piecing together outputs from diverse instruments, each prone to environmental interference. Earth-based scopes battling air distortions and climate, orbital telescopes enduring radiation and heat swings, radio networks navigating ionosphere quirks. When these setups yield marginally varying outcomes, distinguishing true astronomical variances from tool or setting influences gets tricky. The quartet of CMEs hitting this week layers on extra hurdles. Any data captured in this period must adjust for heightened noise levels, potential device impacts, heightened doubt, and recalibrations. This doesn't render the data useless, but it does widen the margins of error, fostering greater vagueness around Atlas's true dynamics. A persistent timing puzzle also bothers me. If clear-cut spacecraft views of Atlas are out there, if images exist to settle the debates we've raised, why withhold them amid a week where space weather offers a handy excuse for holdups or glitches? It'd be ideal to declare, we aim to share sooner, but the CMEs tangled our analysis. Take a look at this. The lack of any such update stands out, even if it doesn't scream trouble. Space weather embodies the built-in limitations we encounter in decoding celestial events. The conditions linking us to the target, the gear to the storage, the capture to the release, all inject interference, voids, and doubts. Certain aspects stem from inherent physics, others from tech boundaries, and some could tie to organizational or operational choices. That's how datasets are managed and disclosed by groups with their agendas and limits. Overcoming these sightless spots calls for backups, varied tools, alternative viewing methods, and separate reviews of identical datasets. It requires openness on observation timings, quality markers, and workflow details. And it demands an ethos where probing data origins feels like coarse science, not confrontation. Part 10. Gear, Prejudices, and the Repository. Our inherent sightlessness. Consider the journey an observation takes from photons striking a sensor to accessing the final data. This routine, unsexy process shapes our cosmic insights. It's riddled with spots where details vanish, degrade, or fail to reach the open. Begin with the sensor. A photon lands, releases energy, triggers a response. That response turns into a digital readout, a figure denoting intensity at a given pixel and moment. Information loss kicks in right away. The shift introduces static, rounding mistakes, uneven responsiveness across the array. Cosmic rays and ions bombard the chip nonstop, spawning bogus spikes needing detection and excision. Faulty pixels, inactive ones, line flaws, all imprint non-celestial artifacts. Compression follows. Unprocessed sensor shots are massive. One detailed snapshot could span hundreds of megabytes. A probe might churn out thousands over a session. Bandwidth falls short for transmitting every bit. Data streams from spacecraft to Earth often arrive in a compressed form to manage bandwidth constraints. This can involve lossless methods that retain every bit of detail or lossy approaches that discard elements considered non-essential. Decisions on compression levels and targets directly influence the scientific insights extractable down the line. Another hurdle is the limited onboard storage. Probes operate with constrained memory banks, unable to hoard data indefinitely. Incoming observations fill these buffers, linger until transmission slots open, and then typically get erased to accommodate fresh inputs. Should an intriguing event occur without earning top priority status, and if the capture period ends prior to sending, those recordings could vanish permanently, overwritten and unrecoverable. Transmission timetables represent yet another bottleneck. Slots in the deep space network are highly valued and scarce, with numerous probes and operations vying for airtime. During allocated windows, craft beam down content in a sequence dictated by ground teams. Vital engineering stats to confirm operational integrity come first, followed by core scientific payloads, supplementary findings, test shots, and extras as per the planner's hierarchy. If a particular target ranks low, its records might sit queued for weeks or even months before heading earthward. Upon arrival, datasets feed into archival workflows that demand further refinement. Unprocessed images convert to uniform specifications, with tags added for essential details like object positions, capture timestamps, integration lengths, wavelength selections, and reliability indicators. This tagging proves vital for future queries in the repository. Inaccurate labels can render files functionally invisible, despite their presence in physical storage. Over time, collections undergo restructuring, shifts to updated hardware, and catalog refreshes amid tech upgrades. Every such transition risks introducing glitches, corrupted files, alignment discrepancies, or severed ties between content and descriptors. In sprawling repositories holding millions or billions of entries, a certain percentage inevitably suffers from degradation, faulty annotations, or retrieval barriers stemming from systemic faults. Proprietary holds and access restrictions add layers of complexity. Project crews frequently enjoy sole rights to their outputs for extended periods, spanning months to years, prior to general availability. This safeguards the innovators behind the hardware and protocols, allowing them leeway to scrutinize and disseminate discoveries ahead of rivals. While sensible, it keeps potentially groundbreaking material tucked away in limited access vaults, out of reach for wider scrutiny and validation. Administrative hurdles exacerbate these challenges. Public dissemination demands effort, curating packages, drafting guides, ensuring accuracy, and configuring portals. Agencies and facilities frequently grapple with slim teams and heavy loads, leading to postponed rollouts. Marginal datasets can idle in private holdings indefinitely, overlooked due to bandwidth shortages in handling and distribution. History offers cases where key records resurfaced from vaults long after acquisition. Fresh looks at Hubble's stored visuals have uncovered overlooked celestial bodies from initial reviews. Voyager's analog reels turned up in lockers years on, safeguarding views presumed erased. Hobbyists, too, have spotted comets and rocks in open datasets that experts initially bypassed. The cosmic repository is immense, defying exhaustive manual inspection across all captures. This inherent oversight permeates the field of astronomy universally, beyond just the Atlas case. Humanity glimpses only the fraction of reality that aligns with observation chances, reliable transfers, meticulous cataloging and annotation, and eventual probing by equipped investigators. Reality passes through this gauntlet, leaving unknowns in the shadows. In the context of Atlas, these dynamics carry specific implications. For one, discrepancies across tools may stem in part from processing biases. A detector might overlook sprawling auras since its routines favor pinpoint star measurements over diffuse features. Terrestrial scopes could bypass dim appendages if their algorithms presume compact origins. JWST excels at detecting gaseous signatures via its finely tuned spectrometers, yet lacks broad surveys to map particulate patterns. Moreover, the lack of Psyche visuals in open holdings might trace to any number of routine snags or backlogs, without invoking secrecy or suppression. That said, accounting for the gap doesn't ease the irritation. Existing captures warrant open pathways for review. Absent ones demand clear explanations for skipped opportunities. Process openness rivals the records in value. Finally, for probing Atlas or parallel puzzles, this points to a savvy approach. Venture beyond formal papers and sanctioned drops. Probe the depths of access public records straight from the source. Grab unprocessed image frames where possible and reanalyze them under alternative conditions. Hunt for anomalies in metadata that could signal incorrectly tagged readings. Cross-reference logging entries with the stored datasets to spot mismatches. Submit formal data requests and Freedom of Information Act filings to urge agencies toward more transparency. Community-driven science plays a key part in this effort. Hobbyists in astronomy and data analysis, free from the limits of professional commitments or job risks, can raise inquiries and conduct investigations that insiders might sidestep. They can team up with diverse groups, exchanging datasets and techniques. Astronomy's past is full of vital inputs from non-professionals, and today's digital tools make such involvement more accessible than before. The systemic oversight is genuine, yet it can be overcome. It demands tenacity, expertise in tools, and readiness to deal with administrative hurdles. It calls for forming alliances among those passionate enough to tackle the tedious task of excavating old data. And it insists on sustained advocacy for organizations to enhance their data handling processes, timelines for release, and openness, since the information is out there at its core. Light particles struck sensors, readings were captured, digital files are kept in some repository. The real issue is getting hold of them, validating them, and examining them in the open. That's as much about governance and focus as it is about science. Section 11. The pursuit of data. Concrete, urgent steps for investigation. We shouldn't merely theorize and hope others step in. Here's a detailed, sequential guide for tracking down the records that might unravel the puzzle surrounding 3i/Atlas. This serves as a blueprint for anyone committed to following through. Start by pinpointing the exact viewing periods. Compute the specific coordinated universal time moments when 3i/Atlas would have entered the Psyche probe's possible observational range. You'll need orbital data for both, which you can obtain freely from JPL's Horizons system and similar resources. Horizons delivers accurate location and speed figures for celestial bodies at any specified epoch, factoring in orbital influences and sighting angles. Figure out angular distances, observable intervals, and optimal alignments. This involves assessing when Atlas and Psyche aligned so the probe's tools could capture the asteroid. Factor in elements such as solar positioning, which impacts lighting and safe pointing of delicate sensors. Include the probe's orientation limits and activity patterns across mission stages. Pin down the particular occasions and durations when Psyche's optics might have aimed toward Atlas, whether on purpose or during standard checks. Probes frequently take navigation photos, setup routines, or diagnostic scans that cover broad sky areas. Atlas could show up in those shots, even unintentionally. Extend the review from Psyche's launch up to now, focusing especially on periods when Atlas was prominent or ideally placed for viewing. Next, review the gear details and output formats. Psyche has designated imagers with defined scopes, detection thresholds, and usage settings. These details appear in official papers, like instrument descriptions, planning outlines, and reports on NASA's technical repository or project sites. The imaging system's parameters cover resolution per pixel, wavelength coverage, noise and readings, and standard integration lengths. Assess what those devices could pick up at various faintness levels and durations. This entails estimating Atlas's apparent magnitude over time. Consider its separation from the sun and psyche, viewing phase, and any outbursts that could boost or dim its signal. Weigh these estimates against the imager's stated detection boundaries. Determine if Atlas was sufficiently luminous and proximate to yield a valuable shot. This clarifies if a capture was viable beyond mere positioning. A dim target across a large view might register in extended shots, but vanish in quick test images. On the flip side, a vivid one could overload sensors without tweaks to timing. Grasping these operational boundaries reveals anticipated outputs and potential oversights. Then, comb through available repositories methodically. NASA's Planetary Data System holds outputs from space endeavors. While the setup follows norms, it can be tricky to navigate, with files sorted by project, tool, and timing via mission-specific labels. The PDS employs nested folder systems, and grasping the layout logical reasoning plays a key role in conducting efficient data hunts. Query using instrument titles, date intervals that span the previously pinpointed windows based on target positions. Retrieve accessible image inventories and metadata directories. These listings offer concise details on every observation, avoiding the need to pull complete image datasets, which keeps large-scale queries practical from a computing standpoint. Employ custom scripts to scan file names, headers, or notes for references to Atlas, interstellar bodies, calibration points, or routine field scans that coincidentally cover the desired locations. Tools in Python such as Astropy and the Planetary Data System Reader can handle PDS file types and streamline scans over vast numbers of documents. Pattern matching with regular expressions helps identify diverse naming conventions potentially linked to the target. Make the archive review thorough. Go beyond clear hits. Examine engineering outputs, calibration shots, and discarded data that could have been omitted from main scientific repositories. Valuable insights often lurk in auxiliary datasets or items flagged as low quality. Fourth, submit official data inquiries. When archive dives yield nothing, file Freedom of Information Act petitions for targeted observations. Stay exact. Demand every unprocessed image from Psyche's imaging systems during the estimated viewing periods, plus related metadata, device records, and quality evaluations. Precision is vital in such petitions. Broad appeals lead to unclear replies or holdups as organizations ask for details. Agencies must address FOIA submissions, although replies could be postponed or invoke exceptions. Typical waivers cover national defense, confidential details, or unprocessed materials. A denial still reveals if records exist and the rationale for withholding them. The reply schedule and exemption category can offer clues. Explore global data access options too. For non-U.S. partners, bodies like the European Space Agency, JAXA, and others follow distinct policies and submission processes. Joint efforts among agencies may be required if Atlas sightings involved overseas collaborators. Fifth, compare against operational journals. Spacecraft routines produce detailed records. Pointing information from attitude systems indicates the craft's orientation. Energy records reveal instrument activation times. Transmission logs detail data transfer moments. These technical documents enable a precise timeline of the vehicle's status and functions. Portions of this telemetry get stored and are obtainable via proper routes. Control hubs keep full journals for diagnostics and operation reviews. Though in-depth telemetry may not sit in open repositories, it persists and can be obtained through official means. If journals confirm the imager was active and aimed at Atlas's position, yet no visual surface in the archive, that's an inconsistency demanding deeper probe. Such voids could signal transmission errors, storage issues, or choices during handling that sideline specific captures from storage. Each cause carries unique consequences and points to tailored next steps. Sixth, review integrity checks and revision tracks. Electronic documents include checksums, hash codes ensuring file wholeness. Reputable repositories track these alongside update logs noting addition, edit, or swap times. Such details are essential to confirm no corruption or interference occurred, and trusted systems provide clear lineage records. Seek checksum records for key eras. Spot voids, oddities, or items with update times post-initial storage. This uncovers potential edits, removals, or flaws needing rework. Valid reworking is common with better calibrations or error fixes. Yet trails must be recorded and open. If data spans various sites, match checksums across copies. Mismatches imply integrity flaws or sync failures. Align file dates with operation event records to confirm if changes match known rework events. 7th, rework public images at hand, regardless of missing Atlas-specific ones. Grab and examine all Psyche visuals from applicable eras. Current processing techniques can uncover details overlooked by standard pipelines. Align them into stacks. Hunt for dim features. See if Atlas shows up in peripheral areas, even if not the main focus. Deploy advanced spotting methods, like AI-driven object detectors, or any tool to spot subtle items that initial automations ignored. Deep learning models, such as convolutional neural networks fine-tuned on asteroid patterns difference imaging techniques, along with CCD and comet photographs, help spot subtle shifting targets amid stellar backgrounds. By deducting standard star field templates, these methods can emphasize fleeting or relocating entities. Scrutinize accompanying metadata thoroughly. Occasionally, items show up in photos yet escape catalogs due to insufficient brightness to activate automatic detection limits, or because their movement caused them to look like glitches. Manual review of potential hits can uncover authentic bodies that computer algorithms dismissed as interference or cosmic ray strikes. 8th, assemble a grassroots review alliance. Handling this alone is overwhelming. Rally a joint initiative uniting hobbyist stargazers, analytics experts, planetary specialists ready to offer insights, legal experts familiar with procedural matters, and coders capable of developing utilities for repository exploration, assigning responsibilities, exchanging discoveries, and ensuring openness in approaches and outcomes. Leverage shared platforms such as GitHub for distributing scripts, Slack or Discord for team syncing, and online repositories for spreading datasets. Set firm guidelines for record keeping. This way, all contributions can be checked and expanded by fellow participants. Hobby astronomers have demonstrated impressive prowess in comparable ventures. Unearthing orbiting extrasolar worlds, sorting stellar systems, and tracking fluctuating lights have all gained from volunteer-driven initiatives. The blend of widespread involvement and diverse skills frequently reveals oversights that solo investigators overlook. 9th, explore informant pathways. Should records be present but wrongly suppressed, internal sources may hold clues. Create protected messaging routes for possible informants to disclose details without revealing identities. Proceed with caution, implementing robust checks to avoid fabrications. Yet authentic disclosures have exposed vital details in previous research disputes. Employ secure messaging applications. Develop assessment procedures to evaluate reliability and safeguard informant privacy stringently. Informant safeguarding demands both digital safeguards and procedural rigor to avoid accidental exposure via file details or activity traces. Anticipate misleading trails. Unnamed routes draw both truthful intel and intentional deceptions. Confirmation remains crucial. All assertions need validation against confirmed data, and bold assertions demand compelling proof prior to acceptance or widespread sharing. 10th, couple the investigative search with community advocacy. Contact observatory leaders, project lead researchers, grant organization executives. Push for transparent data guidelines, quicker dissemination timelines, and enhanced repository access. Research bodies react to public engagement, and showing widespread concern for these issues can sway allocation choices. Harness online networks, scientific reporting, open discussions to build visibility. At times, organizational stagnation yields to societal curiosity when in-house pushes fall short. Widespread appeal can spur organizations to dedicate funds to archival excavations that would otherwise linger unprocessed in storage. Collaborate with outreach experts who can reframe complex topics into engaging tales. The narrative of pursuing concealed sightings of an enigmatic entity holds appeal outside expert circles. Wider focus can yield funding and backing that isolated internal efforts cannot achieve. This demands endurance, expertise, and perseverance against administrative hurdles. Yet it's achievable. Each phase is practical, relies on available resources and protocols, and draws from prior archival pursuits. The issue boils down to whether sufficient individuals are motivated to commit the energy. The rewards could be substantial. Should psyche snapshots of Atlas be located and retrieved, they could resolve the matter conclusively. Detailed depictions of the entity's shape, composition, presence, or absence of a trail, artificial traits versus organic ones, that evidence, if available, bridges conjecture to certainty. And if no such records surface, if the search yields nothing, that insight holds worth as well. It reveals overlooked chances, divergent focus areas from our ideals, untaken prospects. Such knowledge guides upcoming surveillance strategies, campaigns for shifted project emphases, and reflections on observational selections. The pursuit begins immediately. Resources are at hand. Approaches are straightforward. Required now is the determination to follow through and the collective backing to sustain it, for solutions arise not from idleness, but from excavation. Part 12. Validation experiments. Which fresh sightings could refute or validate rival theories? Even without recovering the psyche files, options remain. We can conduct tests still. This setup would help differentiate among the rival theories on the true nature of Atlas. Allow me to outline the key experiments, the measurements they'd involve, and the outcomes that could confirm or discard each theory. Experiment 1. High-resolution polarimetry across various phase angles. Polarization tracks the oscillations in light's electric field, with distinct materials altering it in unique ways. This core attribute of electromagnetic waves offers a robust method to probe surface makeup and texture remotely, without any physical contact. Dust grains diffuse sunlight via polarization patterns tied to their dimensions, makeup, and form, physics that's thoroughly mapped out. Unpolarized sunlight striking a grain results in partially polarized scattered light, where the extent and direction of polarization disclose details about the diffuser. Metallic or crystalline exteriors yield polarization profiles unlike those of porous clumps. Polished surfaces behave differently from jagged ones. Ice grains display their signature traces. By viewing Atlas from varied phase angles, the angles formed by the Sun, the body, and Earth, and tracking polarization shifts across those configurations, we could deduce surface traits with impressive accuracy. Phase angle plays a crucial role since scattering varies by observational setup. Forward, backward, and lateral scattering generate distinct polarization profiles. A match to standard comet dust would bolster the organic origin theory. Decades of comet dust analysis give us clear benchmarks, phase angle trends, levels of linear polarization, wavelength variations. Patterns aligning with metals, ice grains, or engineered forms would stand out as odd. Synthetic exteriors could exhibit exceptionally strong polarization or structured motifs at odds with haphazard grain scattering. The gear is available, polarimeters on major earthbound scopes, or perhaps HSD with approved slots. The tech is refined. What's required is focused viewing slots and precise tuning to detect nuanced polarization variances. Experiment 2. Narrowband photometry in quiet periods. Most gas observations of Atlas occurred around perihelion, when sun warmth sparks outbursts. That's typical. Bodies shine brightest sunward, drawing the bulk of telescope focus. Yet this perihelion emphasis might overlook vital signs of Atlas's outburst drivers. Monitor it sunward at greater distances with narrowband filters targeting precise molecular emissions. Think carbon monoxide, carbon dioxide, water vapor. These filters, often mere nanometers broad, filter continuum glow to spotlight emissions from targeted molecular shifts. For a standard comet, emissions plunge sharply far from the sun in the chill. Comet activity versus solar distance links are firmly set. Past roughly $3 water emissions halt. Others linger longer, but dwindle too. Persistent emissions where none should appear, robust gas output sans solar warmth, call for scrutiny. Natural mechanisms like trapped warmth or decay heat could explain minor holdovers, but bounds exist. A comet's core holds some heat, specific isotopes generate some, but insufficient for hefty gas release afar. Notable bursts beyond $5 would stun and imply rare materials or inner power surpassing solar input. The watch should cover several orbits, following Atlas from perihelion to aphelion and return. Log outburst onset, crest, and fade. Chart the activity profile against solar range. Breaks from norms hint at core makeup and power origins. Experiment 3. Intensive image accumulation using adaptive optics or orbital scopes. Secure the sharpest views feasible. Combine scores or hundreds of shots to boost faint feature detection. Stacking images is a reliable approach. Merging numerous frames cancels random noise as true signals build. Subtle details hidden in lone shots surface in stacked depths. Deploy adaptive optics on behemoth ground scopes like Keck or VLT to counter air turbulence. These setups gauge atmospheric distortions live and warp pliable mirrors to offset, delivering near-diffraction sharpness. Seek JWST or HSD slots for photometry beyond mere spectral work. Orbital platforms sidestep atmospheric interference fully and access bands Earth's air absorbs. Its surroundings. Should Atlas exhibit any expansive features, traces of symmetry, or geometric characteristics, high-resolution deep imaging would uncover them. A perfectly symmetric point-like source would stand out as atypical. Natural bodies inevitably possess asymmetries, however faint. For instance, comet cores are irregular in form, asteroid exteriors riddled with craters, and even seemingly balanced entities display uneven illumination over their exteriors. Seek out streams, outflows, envelopes, the common hallmarks of active comets. Additionally, scan for structured forms, linear boundaries, or consistent contours. Capture images across various spectral bands to distinguish particulate haze from gaseous outflows. Develop composite visuals that highlight material differences. Employ subtraction techniques, contrasting snapshots from distinct moments to emphasize alterations. The imaging demands are stringent. Resolving details at the nucleus's own dimensions, potentially reaching tens or hundreds of meters, calls for orbital observatories or premier terrestrial scopes equipped with superior adaptive optics functioning in optimal settings. Test 4 involves synchronized observations across multiple wavebands. Arrange a collaborative effort with radio arrays, X-ray orbiters, visible light setups, all targeting Atlas concurrently during a phase of heightened activity. Such an initiative demands inter-site collaboration, meticulous scheduling, and approval from scheduling panels for what amounts to an exploratory hunt. The aim is to identify linkages. Should visible flares match radio bursts, it points to electromagnetic processes exceeding mere heat emission. If X-ray bursts correspond to gaseous outbursts observed in spectra, it indicates particular plasma dynamics producing energetic light. Independent fluctuations across bands align with disorganized natural dynamics, where varied mechanisms evolve on separate timelines for disconnected causes. Yet, aligned patterns spanning disparate spectra would be remarkable, demanding coordinated energy discharge systems. Chaotic natural events rarely exhibit strong ties across widely separated wavelengths without a shared initiator or structured energy transformation. Timing of observations is crucial. Certain events occur over minutes or hours, necessitating unbroken surveillance. Others develop across days or weeks. The program must offer ample temporal sampling to capture fleeting occurrences while ensuring extended tracking to define standard patterns. Test 5 entails monitoring for neutrinos and cosmic rays in tandem. This proves challenging due to reliance on fortune and entry to neutrino sensor feeds. Neutrinos prove elusive to spot, demanding enormous detectors buried far below ground or beneath polar ice. The vast majority traverse Earth undetected. Spotting rates remain sparse, with many signals stemming from atmospheric noise or remote cosmic origins. Still, approach KM3, IceCube, and similar installations to note any neutrino signals aligning with Atlas viewing slots. These systems record each incidence with exact timestamps. Once permission is obtained, querying their archives for matches is a simple computational task. Examine cosmic ray sensor grids for surplus incidents during Atlas's energetic phases. Facilities such as the Pierre Auger Observatory and Telescope Array provide nonstop vigilance for ultra-energetic particles. The odds of accidental overlaps can be estimated. Based on spotting frequencies and viewing periods, we can calculate anticipated chance alignments. A compelling statistical link would stun observers and promptly classify Atlas as a potent high-energy cosmic event. Comets produce no discernible neutrinos or cosmic rays. Should Atlas generate them, its underlying mechanisms surpass conventional cometary behaviors. Detection thresholds constrain possibilities. Without significant neutrino or cosmic ray output from Atlas, nothing will register. Nevertheless, the rewards, clear proof of accelerated high-energy particles, warrant the work, particularly as probing prior detector logs demand scant effort. Test 6 focuses on rotational dynamics and photometric curves. Both comets and asteroids spin, altering their luminosity as varied surface regions confront the Sun and telescopes. This core aspect of solar system mechanics offers yet another analytical avenue. Thorough photometric profiling can disclose spin cycles, tilt directions, and occasionally basic form approximations. Regular cyclic shifts in Atlas's brightness, along with their duration and extent, disclose details on its configuration and rotation. Brief cycles imply a compact solid entity. Extended cycles may signal a sizable form or gravitational binding to an outer force. Pronounced swings indicate a stretched or uneven profile. Minor shifts point to a rounder form or an observational angle aligned with the spin axis. An exceptionally consistent curve, overly uniform without typical deviations, would irregularly tumbling objects exhibit light curve variations, which would be expected. Authentic asteroids and comet nuclei display surface irregularities, patches of light and shadow, and elevation changes that cause inconsistencies in brightness patterns. A flawlessly even light curve hints at either an exceptionally even exterior or deliberate adjustments to counteract inherent fluctuations. Should these variations align with other signs of activity and patterns implying deliberate management over random motion, that would be extraordinary. For example, if bursts of gas release consistently happen at particular points in the spin cycle, it points to targeted outlets placed with intent. If shifts in luminosity precede or follow rotational phases in manners that defy simple passive warming from the sun, it signals deliberate mechanisms regulating the output. The monitoring initiative demands ongoing observation across full rotational cycles, potentially lasting from hours to days. Robotic observatories and photometric observation arrays can deliver uninterrupted data streams. Facilities spread across various longitudes guarantee round-the-clock surveillance. Data processing follows proven methods for identifying periods and reconstructing light curves. Test 7 involves detecting magnetic fields through Faraday rotation. As radio signals traverse ionized plasma under magnetic influence, their polarization rotates in proportion to the field's intensity and the plasma's density. This phenomenon, rooted in fundamental electromagnetism and confirmed in numerous cosmic settings, offers a straightforward way to measure magnetic fields. Should Atlas possess a magnetic field alongside an ionized envelope, radio signals from background sources viewed through that envelope ought to exhibit this twist. Proper setup is essential. Atlas needs to occult or closely approach a prominent radio emitter from our perspective. Such alignments are infrequent, yet foreseeable via trajectory computations and catalogs of radio emitters. Executing this demands high-precision tracking of polarization for sources along the sight line at various intervals. Readings must achieve accuracy to whole degrees or subdegree levels in angle. Corrections for Earth's ionospheric rotation are necessary, as it too alters polarization, but global arrays make this feasible and could reveal fields incompatible with a typical comet. Natural comets lack internal magnetic fields. Their cores are diminutive and non-ferrous. Any such detection would be groundbreaking, possibly revealing metallic makeup, inner dynamos, or engineered electromagnetic operations surpassing natural phenomena. The field's magnitude and configuration would inform theories on its source. Each test yields distinct forecasts across models. For a standard comet with odd traits, anticipate typical polarization, solar-driven activity, uneven form and spin, absent cross-wavelength links, and no magnetic traces. As a debris cluster, foresee mildly atypical polarization from group scattering, a spread-out yet bounded form, erratic brightness, and no structured electromagnetic traits. For naturally exotic electromagnetic activity, Look for odd polarization, magnetic signals, wavelength interconnections, and operations potentially persisting distant from the sun. If engineered, outcomes defy prediction, but could include symmetrical forms, coordinated actions, spectral outputs alien to nature, and rhythms evoking oversight. Crucially, these tests allow refutation. We can predefine outcomes favoring or undermining hypotheses. Science advances that way, posing forecasts, verifying them, refining views per evidence. What we must avoid are vague observations open to biased readings. Instead, seek data crafted to resolve debates, compel verdicts, and rule out options. This calls for unified action, scheduling telescope access, elevating these inquiries, and commitment from facilities to pursue what may appear a speculative probe. Yet the rewards for science are vast. Either validating Atlas as an odd comet yields fresh comet insights, or uncovering its other nature launches an entirely novel research domain. Opportunities loom. Atlas faces upcoming solar approaches, activation intervals, and fresh chances. Will astronomers grasp them, or will Atlas linger as a puzzling entry among interstellar intruders? Part 13. Should it prove artificial? Repercussions for SETI strategies and research protocols. Let's address the ramifications head-on. Accepting, even provisionally, that 1I/Oumuamua might be unnatural alters the landscape. The paradigms for extraterrestrial intelligence hunts, protocols for managing detections, and validation steps for bold assertions all demand urgent overhaul. Begin by examining SETI guidelines. Conventional SETI efforts focus on scanning for radio transmissions, deliberate beacons sent out by advanced societies aiming to establish contact. These approaches assume that outreach is purposeful, relies on electromagnetic waves at designated wavelengths, and stems from extrasolar planetary environments. However, should interstellar probes be feasible, compact, and plentiful enough to appear within our solar system, the scope of the hunt alters dramatically. Such a device need not transmit signals. It could remain inactive, quietly monitoring or functioning via mechanisms we fail to interpret as messaging. Identification would arise from irregular actions or material traits that defy ordinary cosmic phenomena, rather than from deciphering transmissions. This pivots SETI away from radio telescopes toward visual inspections, spectral analysis, positional measurements, or any technique capable of spotting unusual entities amid the vast array of tracked celestial objects. Sensitivity levels evolve as well. Classic SETI imposes stringent criteria for validating synthetic signals, given the grave professional and societal fallout from erroneous detections. Yet, with tangible objects potentially accessible and visible, the evidentiary standard adjusts. Direct scrutiny becomes viable, yielding diverse corroborating data and experiments impossible with distant radio emissions. The benchmark shifts to whether an item's conduct across various detection methods aligns more closely with engineered origins than natural ones. Governance issues gain immediate relevance. In the event of verifying an artifact, who controls the findings? At present, space organizations oversee their mission outputs. Yet, uncovering extraterrestrial engineering could invoke alternative oversight. Defense entities might seize jurisdiction. Global entities, such as the United Nations Committee on the Peaceful Uses of Outer Space, could stake claims. Practical legal structures for managing such revelations are largely absent. Protocols for scientific revelation remain vague. The International Academy of Astronautics offers SETI directives that detail procedures for addressing artificial signal discoveries, stressing worldwide alerts and expert validation prior to public disclosure. These, however, are optional recommendations, lacking binding force. Moreover, they were crafted with radio-based findings in mind, not corporeal relics. Should a probe photograph an engineered form, who determines the timing and manner of its release? Ensuring data provenance turns paramount. Assertions of encountering non-human tech will inevitably encounter profound doubt, as they ought to. Dispelling such doubt demands datasets of unimpeachable reliability. Untouched images bearing digitally secured metadata. Corroborative sightings from separate observers confirming the event. Public repositories enabling independent reanalysis. Clear protocols outlining each analytical phase. Lesser measures risk charges of mistake, deception, or flawed reading. Global collaboration proves essential yet challenging. Nations pursue distinct space agendas. Varying degrees of openness exist, alongside diverse ties between civilian space programs and armed forces. A find by one country's vessel might be deemed a tactical resource, not freely shared knowledge. Reconciling ideals of scientific candor with security imperatives would necessitate top-tier diplomacy. Past precedents fall short. The 1967 pulse detection sparked brief thoughts of synthetic origins until the pulsar explanation clarified them as spinning neutron stars. The 1977 WOW signal persists as a mystery without replication. Neither instance necessitated the policy framework a confirmed relic would. Perhaps the nearest comparison lies in the international teamwork and regulatory evolution following the elucidation of DNA's helix or atomic fission. Even these, though, fall short of the breadth. Moral dilemmas proliferate. Does a discovered artifact accrue to its finder, to humankind as a whole, or to its creators? Are we entitled to probe it, tamper with it, or initiate dialogue? Suppose it's surveilling us? What if prodding it provokes unforeseeable reactions? Speculative tales have delved into these, yet they transcend mere imagination. Confronting reality amplifies the peril of hasty declarations. Proclaiming engineered origins on shaky grounds could erode trust, hinder genuine SETI pursuits, and foster mockery that complicates impartial assessment of later assertions. Conversely, withholding proof while insisting on escalating certainty might prove negligent if the occurrence holds genuine significance. Striking equilibrium demands nuanced discernment that's tough to formalize. Moreover, public responses must factor in. How might the disclosure of extraterrestrial technology reshape society? Certain individuals would rejoice, viewing it as the pinnacle of human achievement. Others could descend into fear, dreading potential incursions or profound dangers to our existence. A third group might remain doubtful no matter the proof, dismissing it as fabrication or deceit. Balancing these societal reactions while upholding rigorous scientific standards would likely prove the most daunting obstacle. One thing stands out: our existing systems fall short. Should Atlas or similar entities prove to be engineered, we lack the institutional readiness, operational guidelines, or societal readiness to cope. This isn't a reason to avoid exploration or inquiry or to shy away from evidence, no matter its direction. Instead, it calls for establishing those guidelines today, ahead of any crisis, ensuring that when the improbable turns factual, robust mechanisms exist to address it with care. Scientific inquiry progresses through cycles: observing, proposing ideas, forecasting outcomes, experimenting, and refining. This tried-and-true approach has resolved countless puzzles in the past. The key distinctions here involve the high stakes and intense oversight. Each phase would face intense review from detractors seeking flaws. Every assertion must endure the toughest doubt imaginable. Such scrutiny is fitting. Bold assertions demand ironclad proof, and the effort to collect and verify it must be impeccable. Yet we must not allow these hurdles to stall progress. These inquiries remain viable. The sightings are feasible. Any underlying data, should it be there, can be uncovered and scrutinized. What matters is the resolve to chase oddities with gravity, the discipline to steer clear of misguided outcomes, and openness to sustain trust. The foundational structure is already in place. We simply must deploy it steadily, even amid findings that unsettle us. In truth, we're engaged in this pursuit already, whether we admit it or not. Each glimpse of Atlas, each breakdown of its traits, each effort to account for its actions contributes to the probe. The issue lies in our lack of focused, methodical effort that it perhaps warrants. Will we persist with fragmented, disjointed sightings that leave uncertainties hanging, or launch a concerted drive aimed at clear resolutions? If Atlas is man-made or alien-made, we'll uncover that truth in time. Advanced tech imprints traces that endure scrutiny over the long haul. Form, makeup, action sequences, all would disclose their nature under persistent study. The real uncertainties concern the timeline and the chances we squander via delay or chaos. And if it's purely natural, demonstrating that beyond doubt holds worth too, as it expands our grasp of cosmic possibilities. In any case, the pursuit itself advances knowledge. It compels us to hone spotting techniques, enhance information processing, craft superior theories, and grapple with how we'd identify sentience in unforeseen forms. Such matters merit exploration irrespective of Atlas's true nature. Part 14, a wider cosmic tapestry. Are we stepping into an age of grand enigmas? Pull back for a broader view. 3 instances of Atlas defy the norms of observed comets. ESCAP J1832 emits radio and X-ray pulses on a precise 44-minute cycle unmatched by any familiar entity. A 220 peta-electron-volt neutrino hints at energy boosts we struggle to account for fully. Do these stand as lone quirks, or signal a phase where the cosmos unveils its deeper oddities? Reflect on shifts over the past 10 years. Instruments like the Zwicky Transient Facility, Pan-STARRS, and the Vera C. Rubin Observatory sweep vast sky regions often, spotting shifts or motions. Radio setups such as ESCAP and Meerkat watch the heavens non-stop, catching fleeting signals overlooked by prior gear. Neutrino arrays have evolved from modest trials to massive cubic kilometer detectors. LIGO-like gravitational wave facilities have unlocked fresh cosmic insights. Each advancement uncovers features we never imagined. Fast radio bursts emerged only in 2007, not from scarcity, but from inadequate prior searches. Today, we log dozens daily yet puzzle over their origins. Neutron-star collisions stayed hypothetical until 2017, when we caught one via waves and light together. The cosmos startles us because our tools now probe with deeper reach and breadth. AI and machine learning speed this up. Software sifts billions of photos, readings, and brightness plots, detecting irregularities that would burden humans for ages. Consequently, we're unearthing deviations quicker than we can decode them. The list of baffling occurrences expands steadily. The pace of uncovering cosmic enigmas now outstrips our grasp of the familiar ones. Yet a puzzle emerges. Greater volumes of information bring along increased interference. Additional observations lead to more chance anomalies. Instrument glitches mistaken for authentic detections. An uptick in misleading hits. Scanning trillions of celestial bodies. Rare occurrences in a million become commonplace thousands of times over. So, how do you separate true breakthroughs in physics from mere random deviations that pop up in vast datasets? The key lies in patterns and verification. If oddities group around specific object categories, particular cosmic zones, or defined epochs hinting at underlying truth, they merit attention. If irregularities appear haphazardly, showing up sporadically without recurrence, they're likely just background clutter. Atlas stands out as peculiar, yet it's solitary. ASCAP J1832 intrigues, but again, a lone case. The neutrino registers as a single incident. Do they link up? Have we overlooked similar cases? Or are we forcing links onto sparse evidence, inventing ties where none exist? Fresh findings beyond these cases point to broader implications. Scientists have spotted worlds beyond our solar system, boasting atmospheres defying stability, orbits puzzling standard formation theories, and masses implying bizarre makeups. Certain suns flicker unpredictably, akin to tabbies, sparking talk of vast alien constructs until obscuring dust gets the blame. Galaxies appear lacking dark matter or overloaded with it, challenging our views on how they assemble. By 2025, artificial intelligence is speeding up breakthroughs in the stars. Machine learning spots warped light from gravity, pinpoints quirky light signatures, and forecasts star life cycles better than old-school approaches. Still, AI detects only what its datasets prepare it for, lacking examples of glitches or truly odd happenings in the input. These systems could dismiss them or label them as errors. We're growing reliant on methods that might routinely hide the unforeseen from us. At the heart of it all lurks a deeper dilemma. Are we uncovering real oddities or fabricating them via our own skewed perspectives? The cosmos has long been full of the bizarre. Only recently are we peering sharply enough to acknowledge that oddness. Or could weirdness be subjective, gauged by how much data strays from our theories? As theories evolve, they might incorporate today's mysteries. I favor the first view. Reality owes nothing to our gut feelings or outdated 19th century ideas. Quantum weirdness defies logic. Einstein's gravity warps space in uncanny ways. Invisible matter and energy baffle us deeply. Every wave of researchers learns that the world runs on rules that feel outlandish at first, and even after comprehension, they retain an edge of the uncanny. Perhaps this is indeed an age of cosmic oddities. The 21st century might be when our instruments finally reveal the universe in its raw form, brimming with harsh environments, rare mechanisms, immense distances, and forces that strain the edges of known laws. Atlas, ASCAP J 1832, and superenergetic neutrinos could signal the dawn of a far vaster lineup of stellar peculiarities yet to emerge. Or we might be fixating too much on exceptions, spotting designs in chaos, allowing fancy to outpace facts. The sure path forward? Persist in watching, experimenting, and rigorously challenging our bold ideas with solid evidence. Progress in science thrives on embracing potential errors, then scrutinizing them thoroughly to reveal the truth. One undeniable truth: we're amid an extraordinary chapter in stargazing. Breakthroughs arrive quicker than at any point in history. Queries delve further, responses shock more. Regardless of whether Atlas signals something truly deviant or merely quirky, our ability to scrutinize a star traveler up close, ponder its secrets, and craft experiments to unravel it would have read like fantasy decades back. And more such wanderers approach. Borissimua came before Atlas. Projections indicate scores zip through our system's core annually, though most stay too dim to spot. Once the Vera Rubin Observatory hits peak performance, it'll detect them in droves. Every visitor serves as an envoy from distant realms, bearing clues about realms and dynamics we can't reach firsthand. Each offers a chance to question our beliefs and, perhaps, learn we've misjudged basics we once took for granted. This wave of weirdness could barely be underway. That's exhilarating, even if disconcerting, since it signals the cosmos retains mysteries, shocks, and the might to shatter our cozy assumptions, compelling us to rethink the bounds of reality. Part 15, Final Synthesis. What we truly understand, what we ought to insist upon, and the 3 checks that will resolve it all. Let's ground this in the here and now, and let's outline the confirmed facts, distinguish them from uncertainties, and chart the next steps. Here's the established information. The test mission processed more than 9,000 frames from 3i Atlas and detected no elongated coma, treating it instead as a compact point source. This represents reliable, repeatable evidence. JWST along with various infrared telescopes have identified outflows of gas, carbon dioxide, and water vapor, pointing to active volatile release. These findings are equally firm. Observations from earthbound optical scopes have yielded mixed outcomes. Certain ones noted imbalances, while others observed minimal features. The data points are genuine, though the results vary widely. Details from the Psyche probe that could clarify these discrepancies remain unreleased to the public, leaving us uncertain about their existence. Now, the unclear aspects include the underlying process generating gas absent a clear dust trail, the makeup and form of the object's core, whether the discrepancies across tools stem from truly odd traits or merely biases in viewing and data handling, the potential involvement of electromagnetic or plasma dynamics in atypical ways, and if any of the broad-spectrum events we've covered, like ASCAP J 1832 or elevated energy neutrinos, link back to Atlas. Pure conjecture involves notions that Atlas could be engineered or tech-based, that Psyche mission info is being suppressed for motives beyond science, or that a unifying scheme ties various space oddities via unconventional physical principles. Such concepts merit investigation and validation, yet they lack firm backing at present. They're ideas to probe, not established truths. Consider the escalation framework, progressing from ordinary to unusual, from ordinary to engineered. What proof shifts us up each level? The baseline is natural explanations, needing just a feasible mix of materials, form, and surroundings to account for the sightings without new physical laws. Unusual natural demands spotting mechanisms at play on Atlas unseen in standard comets, but aligned with established physics, such as electrical influences or peculiar ice reactions. Engineered status calls for several distinct proofs of actions defying all natural models, forms suggesting intentional creation, and validated data origins excluding mistakes or interference. The key evaluations to resolve this. Evaluation 1 involves archival deep dive retrieval. Secure entry to Psyche probe records or similar mission views from Atlas's visibility phases. Confirm if visuals are available, scrutinize them for shape and form, and validate their tags and handling records. This stands as the straightforward probe, since detailed visuals would reveal the true look, clarifying if it's a standard bumpy core, a debris grouping, or a shaped construct. Challenges are mostly procedural, with modest tech hurdles. Organizational obstacles could be steep, but success comes via determination and official inquiries. Evaluation 2. A targeted all-spectrum joint observing effort. Arrange an initiative for Atlas's upcoming outburst phase, incorporating polarization in visible and IR ranges, spectral tracking of gas output, radio arrays hunting signals, X-ray setups scanning for bursts, and particle sensors checking for matching high-energy incidents. Such a full-spectrum tactic would spot links overlooked by isolated tools, probing for electrical signs, rhythmic or erratic patterns, or outputs exceeding comet norms. Evaluation 3. Linking high-energy occurrences. Keep watch on neutrino arrays, cosmic ray grids, and gamma-ray monitors for any robust ties to Atlas's phases. This probes the wildest theory of Atlas's tie to intense astro events. It's a slim chance, but streams of live data allow prompt review. A detected link would reshape views on the object's identity. None would rule out certain outlandish accounts. As for the 90-day plan, days 1 to 30, form the community review group, assign archive hunting duties, submit FOIA bids for Psyche files and flight notes, and start fetching and reanalyzing public visuals from relevant probes that may have imaged Atlas. Days 30 to 60. Assemble archive outcomes, draft scope bids for the joint watch during the next flare-up, contact neutrino team partnerships for linkage checks, and launch outreach for open data access. Days 60 to 90. Lodge bids, pursue FOIA replies, release initial insights from archive reviews, and set up links with astropros ready to offer skills and equipment. Here's a plan for engagement if you're following this. Got skills in data science? Step up to dig through archives and build analytical tools. On a telescope, even a backyard one? Join in on organized viewing sessions. Legal background? Lend a hand with formal procedures and pulling data from records. Influence or a following? Amplify the call for openness and push organizations to share info. Resources to spare? Back grassroots science projects through donations or group funding. Each effort shortens the wait from puzzle to resolution. At the heart of this tale lies a pivotal moment. An object acts so oddly it begs for answers, with tech ready to deliver them. And now we must choose. Chase it down with real intent or leave it in the shadows of uncertainty. The simple route? Label it an oddball comet and forget it. The tougher one? Admit our ignorance and vow to uncover the reason. That's precisely how science advances. When data clashes with expectations, when familiar theories strain against oddities, you face a fork. Slap on quick fixes or ponder if core ideas need overhaul. Usually, those fixes hold, polishing the established view to endure. Yet sometimes, seldom, the quirks signal bigger shifts, urging a fresh look at foundations. We can't tell yet what this instance means. Oumuamua could just be a comet with quirky traits that we'll eventually explain. Or perhaps it's the initial sign of an uncategorized natural wonder, rare and wild. Or, and this feels like sci-fi, but evidence is needed to rule it out, it could mark the debut detection of an interstellar relic. The odds of that final possibility are slim, sure, but slim isn't nothing, and the stakes are too vast to sideline merely for being unsettling. What stands clear is this: the enigma persists. Resources are at hand. Methods are set. Proof of the extraordinary eludes us still. But the hints pointing to something beyond our grasp are the most compelling we've encountered. That information lurks in stored files or current sky scans. The real issue? Do we muster the shared determination to chase it, the discipline to execute properly, and the boldness to embrace any outcome? Breakthroughs unfold this way, not via lightning insights, but via piling inconsistencies that spark inquiries, probes that track those leads no matter where, and teams that transform sightings into insight. The Oumuamua puzzle draws us in, handing us a part in sorting truth from error. So let's put it through its paces. Insist on the records, conduct the watches, run the breakdowns, and hear the cosmos out. After all, the true regret would be spotting a chance to upend a key belief and opting to avert our eyes. The edge beckons, the riddle calls, and in unseen datasets or upcoming gazes, the truth lingers, ready for unveiling.